Thank you very much for inviting me here, and happy birthday, Mike. So, the first time I think I encountered your work was actually when I was an undergraduate. So I was very excited when I arrived as an undergraduate at MIT to take a course called The Structure and Interpretation of Computer Programs by Gerald Sussman and Hal Abelson. There's a famous book on this that teaches you to program in Lisp and everything. It was just a beautiful course. And I was super disappointed to find that Sussman wasn't going to teach the course because he was off being on sabbatical at Caltech. So I said, okay, and I took the course anyway. And then a couple of years later, some friend of mine told me, well, the guy came back and he wrote a paper when he was away. It was this thing to integrate the orbit of Pluto. You should go take a look because you're interested in physics too. So I went in it, and I looked at it, and indeed there was Sussman. And there was this guy named Michael Douglas on this paper. And I said, oh, okay. And I learned a thing from this paper that I suddenly realized yesterday has kind of stayed with me the rest of my career, not necessarily in string theory, but in the biophysics that I do. And that is that I learned from this paper that if you design a computational device to be adapted to the task it performs, it can be far more efficient and effective at doing it, as opposed to a general purpose computer. And I realized last night just what an enormous fraction of the things I've done thinking about theoretical neuroscience have been about adaptation of computation to the task at hand. I've written a paper practically every year for the last 20 years on this kind of thing. So I had a paper some 10 years ago called Heterogeneity and Efficiency in the Brain, and which appeared in the IEEE proceedings, the proceedings of the IEEE. It's the American Society of Electrical Engineers and so on and so forth. Essentially, the argument being made from information theory was a formalization of this idea that specialization of computation produces efficiencies, and that is why, that was supposed to be a theory of why there are so many types of cells and computational structures in the brain. So I'm sorry to say, Mike, in all of these papers, I have never cited your paper on the digital orrery, possibly because I forgot the original chain of reasoning that brought me to this. But the next time I write a paper on this kind of thing, I will be citing your paper on digital orrery, on the digital orrery. So thank you very much for that. So the second part of this anecdote is then I decided that, I started as a PhD student in engineering, in computer science actually, and kind of decided after a year or so that I was clearly more of a scientist than an engineer. So I switched to doing a PhD in physics. And then there were these papers that kept appearing by this guy named Michael Douglas, and they were all totally intimidating. They started with abstracts like last week or yesterday, Sen said, and said stuff that I didn't even imagine could be said, right? And I didn't make the connection. Then towards the end of my PhD, I was invited to go visit Rutgers. And this guy named Michael Douglas says, oh, and I was in awe of him, said, well, actually, I think I might want to talk to you a little bit about the work that you've been doing in things like computer science. And I was like, what? And that's when I found out that two Michael Douglases were the same Michael Douglas. So being a string theorist, the natural deduction was all Michael Douglases are the same Michael Douglas. But that was incorrect. But anyway, so thanks very much for everything I've learned from you in all the fields over the year, Michael. So today, I'm actually going to take time to talk about another topic that I know Mike has been interested in for many years, which is the theory of complexity. So I'm going to talk about this is green. Nothing wrong with green. I'm going to talk about quantum chaos and complexity. And complexity theory is another topic that I know Mike has been interested in for a very long time. In fact, the first appearance of complexity theory in string theory that I saw was a paper, I think, that you wrote about the possible computational hardness of finding vacua given the, in the landscape. If you want to find the vacuum that describes our world, how hard is it, was the question. So today I'll talk a little bit about notions of quantum complexity as associated with quantum chaos. My original plan had been to do a 3-part talk, but I learned from you, Shamit, that I'm going to do a 1-part talk with just the, as you'll see, with a little bit tacked on at the conclusion about the other 2 parts, and I'll tell you what those are. So what's complexity? Well, why am I interested in this topic? So in many branches of physics, people are interested in the complexity of quantum systems. Let me list a few. So one is in the theory of quantum computation, and simulations of algorithm design, it's clearly very important to know how complicated a computation is. This is a classical kind of question in computational complexity theory. Now, people are interested in complexity in many-body physics these days, partly because it appears that there may be new timescales in many-body physics that go beyond the thermalization timescale. So maybe I should say, why do we care? There's quantum computation. Then there's to many-body physics. So there are new timescales in many-body physics apparently related to the increase of complexity of quantum states. A third reason is the idea that the complexity and complexity growth may give sort of dynamical order parameters that may distinguish theories that are integrable and chaotic in some ways. A fourth reason why in this field we care is coming from holography. So there are conjectures, famously due to Susskind, that the volume or action of various kinds of spacetimes, particularly in the interior of black holes, may have something to do with the complexity of the quantum state, whatever that means precisely, right? And then finally, there is the issue of information in Hawking radiation and why the Hawking radiation is difficult to decode. So there's something complex about the encoding of the prior state inside a black hole. So more generally, we're interested because in quantum dynamics, you can have a situation where simple states become complex states. And this is certainly the case for black holes, complex states. So we would like to understand the process where here's a simple state. This is a gas in ADS. And the gas in ADS collapses to a black hole. And the gas in ADS, while very hard to figure out exactly what the state is not quite as hard as a black hole, where the states are actually hidden, at least semi-classically, behind a horizon. So it's clear that somehow these states are easier to think about than these states. Let's see why. So suppose we were talking about the ADS-CFT correspondence, and we think about ADS-5. Then the black hole is dual to, well, the ADS-5 spacetime is dual to the n equals 4 super Yang-Mills theory. And this has fields A mu, 3 adjoint scalars xyz, and some fermions. So let's remind ourselves what a black hole microstate is. So in the dual field theory, I should think about some operator O delta acting on the vacuum. And what's the dimension of the operator? The dimension of this operator O delta will be like something like of order n squared in order for this to, so this is an SUN, I should have said, there's an SUN Yang-Mills theory. So the dimension of the operator is of order n squared. So it's a very heavy operator. So what does such an operator look like? The operator will look something like this, leaving aside questions of where I sprinkle the traces and the determinants and other kinds of things. It's going to look like, well, there's going to be some A mu's, X, Y, Y, I don't know, A mu, some derivatives, and so on and so forth, size acting on the vacuum. And so you can easily argue that if I leave aside the question of the traces and the determinants and how you make this gauge invariant and so on and so forth, almost all operators of such large dimension are random polynomials. And so even if you include the traces, they're random polynomials of traces, fields, and derivatives. So there's going to be, so this is some old work with Jan de Boer, Joan Simon, and Vishnu Jejala. Okay, and so we see that if you think about the gas as a simple state, and it's a simple state because I could have made the gas by taking the same operator, an operator O of dimension 1, and applying it delta times to the vacuum. I could have made the state like that. This is supposed to evolve at time, as time passes into the black hole, which is this complex state, indeed a pseudo-random state of some kind. So it's worthwhile asking the question, how is this complexity generated? Because if I were to think about this as a process, there's some, you can think about it as a quantum computation that takes the initial state and does something to it systematically, indeed through apparently local operations even, and produces this very complicated state. And that very complicated state does all the weird black hole-y things that we butt our heads on. So how does this happen is a perfectly worthwhile thing to ask about. So in order to ask this question, the first thing you got to say is, what does the word complexity even mean? Because that's the kind, it's a word like good, right? It means many things to many people. So what does complexity mean is the question we need to ask. And that's relevant for all of these. So for example, if you consider the holography, whatever, complexity equals volume, I mean, these things are sort of empty statements unless you define both sides of something equals something. So you got to start out by saying what complexity means. So let's investigate the possible meanings of the word complexity in this field. So let's work out some intuitions. So the field where people have studied the notion of complexity more than any place else is indeed computer science. It's been a primary topic of investigation to ask, what does the complexity of a process or a system or whatever else mean? So let me remind you of how they think in that field. So there are many definitions people use, but all of them have the following character. You have a thing, X, and you want to know what its complexity is. And pretty much the way people define it is they define it as the minimum number of simple building blocks you need to build X. So you start out by declaring that, not that you necessarily know what the complexity is, but that you know what simplicity is. You say what a simple thing is. And that could mean different things in different situations. So for example, in a physical theory, you might declare that local operations by low dimension operators are simple. That maybe that's your definition of locality. Or that if you have a qubit system, that things that act on small numbers of bits at the same time are simple. Pick your poison. And then given that, you can decide that the complexity is understood by saying, if I want to do the big thing, how many small things do I need to put together? Like you make a castle, it's complicated because you needed many bricks. That's the idea. There is, of course, a fundamental ambiguity in this statement. And the ambiguity is what simple building block should you use? And that's one of the questions that I will talk a little bit about today. So let me give you two specific incarnations of that problem. There's a camera there, so I suppose I should just stay on the central board. Okay, so let me give you two incarnations of that problem. Here's one way in which that problem appears. So suppose you want to study the complexity of time evolution, which is kind of what we want to do. What would you do? Well, so one way of thinking about this is you can consider the SUN group, right? On n, suppose your Hilbert space is n-dimensional. And then you are talking about evolution is on the SUN group, time evolution of the SUN group. You start out at the identity. You apply e to the minus IHT. You get some unitary operator U of t. And the computation being done, in the sense of quantum computation, is a trajectory, a specific trajectory determined by the Hamiltonian on the unitary group. So what could complexity mean here? Well, a reasonable idea would be the complexity here of a computation. By the computation, I mean you need to do U of t. And you're going to do U of t as a sequence of little operations going from one place to the other place. So you might say that the complexity is the length of a geodesic from the identity to e to the minus IHT in a metric penalizing complex operations. By the way, is my handwriting legible? Okay. I'm working famously in the tradition of Mike. Though perhaps I should write on the same board twice. Right. So this is you need to do this in a metric that penalizes the complex operations. So there's an ambiguity here on what you mean by complex operations versus simple operations, and what you mean by the metric. So usually the metric, so Nielsen taught us that if you want to compare with notions in circuit complexity, you should pick the metric to be of order e to the s, which is the entropy log dimension of the Hilbert space in the complex directions. So we actually have a body of work. So because there's an ambiguity of picking what you mean by the simple gates here, by simple operations, simple directions in the motion, and because there's some ambiguity in the choice of the metric, for this reason, computer scientists, when they try to do this kind of thing, will usually report their results not by saying I found a complexity of 3 times this, some precise number, but rather in terms of a scaling law. They'll say if I made the problem so much bigger, n went to 3n, how would the answer for the length of the geodesic scale? Because that scaling law is typically not very sensitive to a choice of gate set and the choice of metric. Kurt, you had a question. Having been your student many years ago, every time you have a question, I can sense it.
Complex directions. So how?
Yes, very good. So let's discuss what complex directions would mean there.
I take it this is not in the base mathematical sense there. It's a different complexity. But
what do you mean the base mathematical sense?
X plus IY. Complex plane.
Oh, certainly not. Oof. We're way past that. So let's say, so suppose you had an n qubit system. Then you might say O is simple if it operates on less than or equal to k qubits at the same time. So that is one example of such a definition. Indeed, this is the example that was originally used by Nielsen in his work. The idea here is that you have a laser that's doing its thing with many qubits. Well, it's certainly harder to work with 5 qubits at the same time, manipulate them, than 2. So if you say if you declare k to be 2, then things that operate in 2 qubits or less at the same time, binary gates are easy. Everything else is hard. And then you can go to town on this. Should you say that it's just easy and hard? Should you have a gradation of hardness depending upon how many number of bits are, what k is? And there are, of course, lots of results showing universality, lack of universality, what the details do, what the details don't do, of this kind of thing. Okay? So I'm actually not going to talk about this today, but I'll just give you, what's that?
Vijay, you answered the question by introducing 2 more notions. So k is what? K is
the number of qubits. So k less than or equal to n is the number of qubits on which the gate.
It's always less than or equal to n. You probably mean that n goes to infinity and k stays finite, or
you can do that if you like. You can do so you can play. We're theorists. You can play many games here. You can say, suppose n is fixed, do your calculation with k fixed, and give me an answer. Then take n to infinity and tell me how things scale with n. Or you could take k and n fixed, do your calculation, then take the ratio k over n fixed and send those to infinity and tell me how things scale. There are different things you can do here.
But your definition doesn't refer to k, so you just say, oh, it's simple if, and then there's another letter here. So maybe you mean that it's k simple or k over n?
Absolutely. I left it ambiguous because people do different things at different times. So if I would define k simple to mean, if I'm doing it working with a qubit system, I would define k simple to mean you have a gate that acts on k qubits or less and sends out 1 qubit. That's what I would mean by k simple or less, and I would say k complex if it's more than k, right? And that's a very discrete definition. So you could, if you like, grade the complexity with k, as an example. This is actually not what I'm going to talk about, which is why I'm being a little bit quick about this. We have a whole body of results about this, which you will enjoy, Mike. So basically, maybe I'll tell, you know what, I'm going to take a few minutes at the very end to tell you what you can do with this. You can write down this geodesic equation. There's a very nice formalism due to Euler. There's the Euler-Arnold equation, which describes geodesics on group manifolds. And you can use it to actually work out the length of these things, prove general theorems about when these lengths will grow long and when they'll grow short and stuff like that. So I'll tell you a little bit at the very end about the possible general theorems that you can show with their applications to things like the SYK model and what they teach you. So I'll tell you a little bit about that. So that's one approach you could take. But I just wanted to point out that there are some ambiguities. There is a related notion of circuit complexity. This is actually the traditional thing that people worked on in computer science, where you have some computation. Maybe I should have written this down first, because it'll be clear what I might want to mean by simple or complex gate here. By the k complexity, as you were saying, of a gate, we mean how many bits come in and 1 bit goes out. So you can write down for any given computation, you can work out let's say the number of gates to do the computation. Or you can work out the depth of the circuit or the width of the circuit. You pick some measure, and that is a measure of complexity. And Nielsen's result was that these two things are related, provided you pick a complexity metric in the sense that I told you. You penalize simple versus complex by an exponential in the log dimension of the Hilbert space. You will get answers that are polynomially related. That is, whatever you get, the answers will differ by polynomial in the problem size. Okay? So this is certainly something you could use, but it would be nice not to have this ambiguity of what the k is, what the simple gate is, what the metric is. So today, I'm going to try for another approach, which is in many ways much simpler than doing this. This is a somewhat complicated formalism, because the SUN group is a complicated fiber bundle. Solving for these geodesics is a complicated problem with many interesting topological features that I can tell you a little bit about at the end. But today, I'm going for something simpler. I'm going to try to resolve this ambiguity in a different formulation of what complexity means, in a different formulation of complexity, and we'll see what we get. You'll see we'll get some very, very beautiful results out of this. So maybe another way of thinking about this is to say something like this. So I'm going to think about quantum mechanics as saying that there is a wave function of some kind defined on a configuration space. And this is like the state. And I want to say that suppose I have a simple dynamics. I might imagine that the simple dynamics looks like this, that the system sort of spreads around in some, quote, simple way in this state space. It occupies somehow, the wave function occupies a relatively small, well-defined, maybe somewhat geometric part of the configuration space. And then I might imagine that a complex, perhaps that means chaotic, kind of dynamics, chaotic, winds up looking more like this. But somehow, at the end of the day, after you evolve for a while, the wave function comes close to everything in some sense in the Hilbert space. So the question is what those senses will mean in a moment. Okay? So something like that would be nice. So in this sense, you might imagine that you could try to come up with a definition of complexity. Remember, we're just feeling our way towards a possible definition. In terms of the spread of the wave function over time. Okay? So what can we mean by the spread of the wave function? Well, if you gave me a basis, I might suppose that in that basis, we would like to know the breadth of support in that basis. So now, of course, there's an ambiguity if I say things that way. So which basis should we pick? So I'm going to argue to you that there's a nice answer you can give for this. That in the spirit of these folks, right, in the spirit of sort of minimizing things, and also, by the way, in the spirit of earlier definitions of complexity given by people like Kolmogorov, that you should pick the minimum, you should pick whatever definition gives you the minimum answer. That's how you define the uniqueness of your notion of complexity. You might suppose that the answer should be that for any initial state, for any initial psi naught, pick the basis B that minimizes the spread over time. So I'm going to start today by arguing A, that this is a well-defined notion, that B, there's a practical way you can do it. C, there's a fast algorithm if you want to do it numerically for doing it. There's even analytical results you can get. And then I'm going to apply this to various kinds of theories that we know are dual to black holes and show that this so precisely the sort of ramping growth and complexity for an exponential period of time and then plateaus and all of the features that we want to know are apparent in this definition.
It's going somewhere in the direction of, okay, I start out with the ground state wave function of hydrogen. It's a little blob at the center, and it's zero out. It's essentially zero outside some radius and not zero inside it. It could evolve over time into something where, the difference between the wave function essentially zero and not zero in this configuration space gets smaller and smaller and smaller. The zeros are just more and more densely scattered.
In some sense, yes. In some weird sense like that, yes. I'm going to try to make a state later. There's a statement we're trying to prove that I'm not going to make definitively today that I'll tell you about at the end. That at least for chaotic theories and for nearly all states up to a set of measure zero, that after a period of time that's logarithmic in the entropy of the system, by which I mean log dimension of the Hilbert space, or if there's an energy band, log of that entropy, that it's going to be the case that there's a sort of universal behavior of the wave function, that the wave function will spread to become nearly the same in some sense for all of these states. And it'll be spread out over, there's going to be a unique basis over which it's effectively spread out. So I'll tell you about that in a little bit.
Vijay, so B depends on the choice of time, or?
B depends upon the choice of initial state.
But going forward in time, it's always the same fixed B?
It's going to be the same fixed B. Otherwise, by this definition, the way I've stated it, I could always pick my state to be in my basis, in which case the spread would be zero.
But so the time, you pick a convention for when you're defining B?
You tell me your initial state. So you give me your initial state, and I'm actually going to describe the complexity of the spreading of this wave function. So I'm going to talk about it as the complexity of the state, because the basis is defined relative to the state. But then the state will spread in some way, and we're going to try to measure how it spreads.
Yeah, I guess what I was saying is, isn't there a convention dependence in how you define spread that will change what B is?
So I'm going to try to tell you that give me a moment. I'm going to try to tell you that you can pick any definition you want, and the same basis is going to be minimizing. Let me show this somewhere. Any definition, any reasonable definition. So I'll define reasonable in a minute.
Sorry, Vijay, I'm confused. An energy eigenstate has zero spread?
Yes. So the energy eigenstates are measure zero going in the space of states. So they are going to be the special cases that only pick up phases and don't spread. But excellent point. So in this sense, it doesn't spread, so it's not very complicated. Indeed, its time evolution is very simple. That's why we like them. But most states aren't energy eigenstates.
Okay. And yet, in a classically chaotic system, chaos means something very different.
We are going to, one of the things I like very, very much about this formalism and about this formalism is that I will show you a precise connection to the classical characterizations, classical and typical quantum and classical characterizations of chaos in the sense of what we know about the spectrum and the structure of the eigenstates. I'm going to show you that this definition connects directly to the structure of the spectrum. In particular, we will see that this notion of spread is connected to the structure of the partition sum, the analytically continued partition sum, in a completely direct way. And then you will see what the connection is to the usual notion involving, for example, in chaotic systems, there's the level repulsion and all of that. All of that will appear directly in this. By the way, it also appears directly in this. And so there's an interesting connection between this. I'm describing this today because it's a very simple idea. You'll see this is extremely easy, as you'll see. And this is harder, but we'll see that they're connected by the very end. OK. So I'm going to define complexity in this sense. And as you'll see, it's all extremely elementary, which is what I like about this. So in quantum mechanics, you know that the time evolution rule is this. So this means that I'm going to take a time-independent Hamiltonian. So I can write the time evolution as a sum n minus it to the n over n factorial psi of 0. Whoops, psi n, where psi n is going to be the state h to the n psi of 0. Okay? So if this was a discrete time evolution, notice after n time steps, I would just keep the nth piece here. Right? We're doing continuous time evolution, so I've written down the e to the minus iht here. So now I'm going to pick a basis b to describe this system. And the basis b, for the moment, I'm going to take it to be ordered. And it's going to have 0, 1, etc. And this is going to be some orthonormal basis. And I'm going to define a functional which is going to turn into a measure of complexity after doing some minimization of the following form. There's some coefficient Cn, and then I'm going to take the overlap of my state at time t with basis element n, magnitude squared, and I'm going to add it all up. And if you like, I'm going to write this as Cn pb of t. We will require one condition, C0 less than C1 less than etc. So Shamit, in answer to your question, for any choice of C's that are increasing this way, I'm going to show a uniqueness property. So one way of thinking about what I'm going to talk about is, so mostly I'm going to pick Cn going like n, and that's to actually connect with some notions of operator complexity that have been used in condensed matter physics. But you don't have to. For example, you could pick n squared, n cubed, whatever you want. Really, the full information about the spread of the wave function lies in these probabilities, if you like. And so really, you want to look at all the moments. Or you could even look at the entropy of this distribution Pn, Pb. And for all of those kinds of notions, if you look at any of the moments or any of these Pb, the statements I'm going to say hold true. Okay? But I'm going to pick Cn equals n because there's a body of prior work in condensed matter physics quantifying the entropy, the complexity of operators in an analogous sort of way with Cn chosen to be n. So that's why I'm going to pick that for most of what I'm going to talk about. Okay? So we're going to define the complexity of the system, given your choice of C's, and pick whichever one you like, or all of them, or whatever you want, to be, I'm going to say C, the complexity is the minimum over all of these bases of C basis of T. Okay? So we need to do this minimization in a functional sense, right? There are all of these B's. You've got to decide what it means to be a minimum. So let me explain that. So suppose I have this CB1 of t, and here's another function CB2 of t. Then I would say CB2 is less than CB1. Okay? So I'm going to do this as follows. So in discrete time, you can do this for all time. But in continuous time, so far we've only been able to get the full proof in Taylor expansion around the origin. Right? So that's what I'm going to do. That's why I set this up like this, as a Taylor expansion around the origin. So we're going to work within the domain of convergence of that Taylor expansion. So I'm going to put SB equals the CB at time 0, dCB dt at time 0, the second derivative b CB dt squared at time 0, and so on. So I'm going to consider the family of time derivatives. The idea here is that if I have two bases and all the derivatives are less, then I can guarantee that there's a period of time over which one curve is below the other. Right? So this is like analysis 101, a chunk of this paper. So there's a theorem. So we're going to say that SB1 is less than SB2 if there is some k such that CB1 of n equals CB2 of n for all m less than k, and CB1 of k is less than CB2 of k for m bigger than k. So what does this mean? So if I got two bases for which the first m derivatives are the same, and then one has lower derivatives, then we say it's less than, because then I can guarantee that the second curve will be lower. So I'm just setting up the condition. But this is...
You mean m in that second.
What's that?
So you want m both times.
I mean m on both. No, I mean k. M. Right. So we want to do this. So OK. So we're going to agree that this is going to be the case. And if this is the case, then there exists some time, t2, such that CB2 is less than CB1. The complexity relative to basis B2 is less than basis B1 over some domain. So that's going to be a fact. So here's a theorem that you can prove for any basis B. There's a special basis called the Krylov basis, which has the property SB is less than SK is less than SB. So K here is something called the Krylov basis. And the way you produce the Krylov basis is by Gram-Schmidt. You do the absolute obvious. You Gram-Schmidt the sequence of states that you produce by applying the Hamiltonian to the nth power. Right? Just do the obvious. You do this, h psi naught, h squared psi naught, etc. And you do that. And you can guarantee that this orthogonalized basis, this orthogonal basis, is the minimizing basis from this notion of complexity. So proving this for the continuous case, is there a way of pulling the top one down? Ah. Wow. Was that? They still haven't invented technology better than scratching a rock on another rock. Easier to read and everything. How am I doing on time? Terribly.
Not so great.
It's OK.
But oh no, you're great.
I have like 15, 20 minutes, right?
Oh yeah.
Actually, I'm in great shape.
Can I ask a question while you're erasing?
Yeah, of course.
So this basis depends on your states. So if you want to start comparing complexity of different states.
Yeah. So that refers to what I was trying to say earlier, that certainly, for example, if you take an energy eigenstate here, you're going to get a complexity of 0 all the time. That is correct. We're going to wind up working with things that look like thermal states because they're spread out over the whole thing, and I'll show you universal results for those. And we have a result that we haven't nailed fully, suggesting that almost all states in the Hilbert space, by which I mean, if you start off with a state that has even the tiniest support on all the basis elements in any basis you pick, that after a very short period of time, the evolution of the complexity looks universal. So, but I won't show you that result today because it needs to, there are some issues that we need to fix. Again, that's it's like writing analysis papers, this. So a little care required. Okay, so let me give you the proof.
Should be some correlation between the way Cn grows, the coefficient Cn,
Yeah.
and the energy eigenvalues.
The Cn, the Cn has nothing to do with the energy eigenvalues. This is by picking Cn equals n. So if you think about this as a wave function that's spreading in a special basis, the Krylov basis, if you pick Cn equals n, you're calculating the mean position of your lump in the basis. If you pick Cn equals n squared, you're calculating the width of the wave function across the special basis. I'll draw pictures of this on the board later. And so you're calculating moments of the distribution over the basis of states. that in itself has nothing to do with the actual structure of the eigenstates.
You mentioned that you mentioned something like in some time this will spread all over, and that time should probably depend on differences in eigenvalues.
It will depend on difference in eigenvalues. The statement that I made had to do with, this is the stuff we've got nailed down, has to do with the difference between chaotic and integrable theories. In integrable theories, you won't spread over all the eigenstates. And in chaotic theories, you will. And we're trying to understand some details of when, wherefore, exactly how you characterize that. So yeah, of course it'll depend upon the differences in eigenvalues, because the spectrum will tell you something about the dynamics. Yeah.
You're about to prove the statement about
Yes.
the Krylov basis.
Yeah.
Okay.
So I won't prove it to you for the continuous case, because it's a headache. But the discrete case is very easy to show, and the continuous case is just an analysis version of that. So let's suppose, so I'm going to compute this for the discrete case. Suppose bi equals ki for I equals 0 to n minus 1. Right? Now, so this means that I have a basis which matches the Krylov basis for the first, let's call it k actually, that matches it for k steps. I'm going to show you that unless you pick the k plus 1th basis element to equal the Krylov basis, you're going to find that bi leads to a higher measure of the complexity. So here's how you do that. Suppose for n less than or equal to k, then psi n is equal to the sum k. I'm going to switch the notation n because that's what it's in my notes, otherwise I'll mess it up. Actually, I'm going to say n minus 1 even. Just keep following my notes. So this is true. Right, so we're talking about discrete time evolution. So, after every step, you've got support on these k basis. So after n steps, these are the k basis elements on which you have support. So you've got all of them, right, up to n, because you've got applied h once, twice, 3 times, 4 times, all the way up to h to the n, or h to the n minus 1. You've applied it a certain number of times. And these are all the basis elements you're going to get from Gram-Schmidt orthogonalization of those. Now consider the next one. Psi, this is n minus 1. Let's consider psi n. Psi n is equal to a piece that's perpendicular to k perpendicular kn, and a piece that's parallel, and I'm going to write this as chi parallel. What do I mean by this? So far you have some state in the Hilbert space. After n minus 1 steps, you apply the Hamiltonian one more time, and whatever you get, you can split it into a piece that lies along and a piece that's perpendicular. And this is your new state. So the best you can possibly do in terms of minimizing the number of basis elements you need to describe the state is you keep the previous part of it, and then you add the perpendicular projection. Right? That's the, you take h to the n applied, so the perpendicular projection is you take h to the n applied to the initial state, and you pull off the piece that's orthogonal to the states you already had. If you picked any other basis element, you would need more of them to expand this state. So for example, if you had picked your next basis element not to point this way, but I don't know, to point that way and that way, then you would need 2 of those to expand this. And because of the definition of this complexity functional involving the CNs multiplying all these states, you would get a larger number because you impose a monotonicity on C1 less than C2 less than C3, etc. Right? So that will be the case. So it guarantees, in this discrete case, it's obvious, it's trivial, that all you should do is you follow your state around. The way that basically the logic of this is you start with this state, please include it in your basis. It evolves a bit and moves that way. Add the orthogonal piece, include that in your basis. Evolve some more, add that piece. So you basically follow the state. You start this, it goes this way, it goes that way. So first you keep this state, then you add that part, then you add that part, and then that's your full state. So you just follow the state around. So for the discrete case, it's completely obvious that this is the minimizing basis for any, this will give you a lower value of this complexity function than any other basis. For the continuous case, obviously it takes a little bit more work because you have to analyze, a sequence of derivatives and how they unbound them and things like this. But you can do that, I'm assuring you. Does that at least give you a sense of why that works out? So now that's all well and good. The question is it useful? The value of any definition is in its uses. Before I talk about the uses, I just want to make one comment that, it can feel in this language a little bit unnerving to have this C1, the sequence of C's, because that feels like it's an ambiguity, right? I have to introduce what these C's are. So let me just tell you an alternative definition you could pick for which this proof also works. So suppose you define P of n and t as being the overlap with my basis elements squared. And I define the complexity to be e to the entropy of P, where h is minus some P log P. So this seems like a very natural definition of the complexity of the system. Take the entropy of the distribution describing the spread in your favorite basis, and then you exponentiate that. So this proof similarly works for that. So then you can feel like you didn't make an arbitrary choices of the Cn. Okay, I'm going to continue to work with these Cn defined as n, again, because there happens to be work in condensed matter physics, which is analogous to picking the Cn's equals n. But that's a comment I wanted to make. So suppose you want to use this as a practical computational tool as opposed to just a set of words. Well, how do you compute the Krylov basis is the next statement. Because in practice, you give me a state, I have to calculate this. So there's a method, a very old method, due to Langsos. There's even a book about this, which describes how to calculate this kind of basis very efficiently. So I will tell you what you do, and you will see whether you want to do it by hand or recursor or on a computer. This is utterly trivial. So you can write down a recursion relation like this. You say, so this is a recursion relation for these Krylov basis elements. And you start with some boundary conditions with the initial state being the first of the basis elements, and you go. Easy. Absolutely easy. So you can, written in this way, the Hamiltonian, if you write it out in terms of this procedure, the Hamiltonian, the action of the Hamiltonian is also very simple. And the action of the Hamiltonian is like this. Okay. This should be n minus 1. Which tells you that in this special choice of basis, any quantum dynamics at all, has a tridiagonal Hamiltonian of the following kind. You can always write, this is one of the things I learned by doing this project, was that you can always write any quantum dynamics in this way as a tridiagonal matrix. Okay? So if you write psi of t, the state is a sum on a bunch of coefficients, psi n of t, times the kth Krylov basis, the element. You can think about this as a simple sort of Markov chain type dynamics. This is basically telling you that no matter what the dimension of your system, of your quantum system, you can always reduce the dynamics to look like the dynamics of a one-dimensional quantum chain. Okay? So if you write it in this way, you get I ddt of psi of t, psi n of t, so n is the nth basis element there, is equal to an psi n of t plus bn plus 1 psi n plus 1 of t. This is an equation for the coefficients, bn psi n minus 1 of t. So you can reduce, so there's a universal one-dimensional chain dynamics in the Krylov basis for all quantum systems. And we're going to use this. Now, the logic of this is getting this goes to the middle.
Sorry, Vijay, I'm perplexed by your statement. So the diagonal is I can diagonalize a Hamiltonian, that's unique.
Yes.
How unique is this whatever you called it?
This tri-diagonal form, how did I get that?
How unique is it?
Well, the Krylov basis is unique. It's unique in the sense of it depends on the state you start with. You tell me which state you start with, and I will give you a tri-diagonal Hamiltonian associated with the dynamics of that state. So it's state dependent. So to get sort of universal results, really universal results out of this, you need to be working in a quantum theory which has some sort of mixing property that you start with some initial state and very quickly the state becomes very like other states. And the thing I won't fully argue today, but the thing that we're going after is that chaotic systems have that character, that you start with any initial state, and very soon the state is in some sense very like other states, and then the dynamics is universal. But even if you're an integrable theory, right, you tell me the initial state, and there's some tri-diagonal form, you can tell me for that initial state always. Right? This is a very powerful thing, and I'll tell you why. So now I'm going to tell you that everything you want to know about the system can be computed from one time-dependent number, which is something called the survival amplitude, the probability that the state becomes stays itself after a time t. So let me show you that. And we're going to use that to actually calculate the complexity. Let me just check the time. We're good. So suppose you have psi of t equals psi n of t, sum on n, times the Krylov basis. And we're going to agree that the survival amplitude is psi of t, psi naught. So S of t basically generates the moments of the Hamiltonian. So if you do dn dt like that, t equals 0, this gives you k naught I h to the n k naught. Now observe that these quantities I h to the n k naught are the things that we orthogonalized to get the other Krylov basis elements. So because of that, there's a trick which involves the action of this so if you can compute the survival amplitude, from the survival amplitude you can calculate whatever you want regarding the moments and plug those into to this algorithm by taking some derivatives. So basically, if I have a state k naught and I k1, etc., you have this kind of dynamics that's looking like this. It's a kind of Markov-like dynamics, etc. And you can solve this dynamics to figure out what is the probability that you never left the initial state. If you know that probability you never left the initial state, you can take derivatives to find out all of these things. And from that, you can solve the Langsos method. So there's a procedure to follow. Okay, so I'm giving you snapshots of this. So what can you do with this? So the next step is to ask, how do you calculate that survival amplitude? So now I'm going to make a connection between the survival amplitude and the partition sum, and then the complexity. So let's consider a thermofield double state for your system. So here we have psi beta, 1 over root the partition sum on n, e to the minus beta en over 2 nn. So I've doubled the system and made a thermofield double state. So this is, of course, invariant under evolution by h left minus h right. because of the way the system has been written down. So let's time evolve this instead by h left plus h right over 2, or just by h left. So if you do that, the way the state evolves, so this is a particular state. So we've taken our system, and we're going to try to compute the complexity and all of these kinds of things. But we're going to do this in this particular state. Remember, you already asked about the state dependence of these things. I'm picking this state because this state is a nice state, and because it's spread out over the Hilbert space to start with. So suppose you start with this. Then psi b of t is e to the minus I h t times this initial state. And notice that what that gives you is psi beta plus 2it. Okay? So the spectrum in this theory is packaged in this partition sum. In the partition sum as follows. So if you have z of beta minus it, this is going to be, this is the analytically continued partition sum. This is e to the beta minus it en. Now I want to make an observation. I'm going to write down the survival amplitude. Remember, the logic here is going to be, if I have the survival amplitude, by doing some Markov chainology and a little bit of computation, you can work out these moments. From these moments, you can do the Langsos algorithm. From the Langsos algorithm, you can work out this Krylov basis. From the Krylov basis, you can work out the complexity.
So okay. What do you divide? So this is a thermophile double?
Yes.
Okay. So what do you divide by beta?
Partition sum.
No, e to the minus b beta en divided by n?
This should be 2.
Yeah, okay.
2, okay.
Thank you. So I'm going to argue next that the survival amplitude is the overlap between psi of beta plus 2it, because that's what the time evolution of the state is, and psi beta, because that was the initial state. And if you work that out, that gives you 1 over z beta, sum on all the states of e to the minus beta minus 2it over 2 en minus beta en over 2 n, which gives you this ratio of z beta minus it over z beta. So what we just found is that for a thermophile double state, the survival amplitude, the chance that the state remains unchanged, is simply related to a ratio of the analytically continued partition sum and the partition sum in the first place. I remind you again of the logic. If you give me a theory for which I can compute the partition sum and analytically continue it, I can work out this number, the survival amplitude. The survival amplitude is the moment generating function for the Hamiltonian. From that, I can do the Langsos business. From the Langsos business, I can work out the Krylov basis, all these coefficients, and work out the complexity in this definition. Kurt's not happy.
No. I mean, this chain was fine. I was just trying to. It seems odd. The definition of complexity seems particularly artificial.
Oh, goodness. I felt it was particularly natural. Why do you feel it's artificial?
Why is this particular dependence of the coefficient c n on n?
Or you could make it n squared, whatever else, but I'll tell you why in a second. So, I really believe,
Monotonic is fine.
well, it'll give you different notions of spread of the wave function. Maybe we shouldn't even call it complexity. I'd be happy to call it, it's an interesting notion of the spread of the wave function. But the case I'm going to make to you in just 2 minutes, because I'm going to, at the conclusion of the talk, right, is going to be,
You get a credit for my lateness, so.
I have 4 minutes, 5 minutes, 7 minutes, 7 minutes, right. So I have 7 minutes. The case I'm going to make to you is, look, the value of a definition. So as I said at the outset, there's been a lot of loose talk about complexity equals this and complexity equals that. So really, to make any sense of any of that, you've got to define what you want to mean. I told you this was a particularly simple definition that didn't a priori have, wasn't related to these things that people have done in computer science. but I'm about to tell you that it produces answers to all kinds of interesting things that match expectations that people had for the growth of complexity. Let me tell you that, right? I'll tell you that in a second. So the way I'd put it is that the value of a definition is in the uses that you can make of it. So for example, again, if you take Analysis 101, in week 1, they tell you about this bizarro notion of the compact set, right? That every cover has a finite subcover. And you think, which idiot would define that and why? And then you find out later that if that's true, all good things in analysis are true, right? So we're going to find out that if you accept this as a kind of notion of complexity, and I'll talk more qualitatively about why you maybe should think about it that way in a moment, it'll turn out many good things turn out to be true. So I'm going to tell you a few of those good things right now. Okay? But it's a fair question, especially because it seems too easy in a way. I mean, all I did was to measure the spread of the wave function in a basis which was supposed to be unique. So now I'm going to tell you some uses you can put to this. But before that, I'm going to summarize everything I've said so far over there, and then I'm going to write down the results here as applied to various systems. So what we said in summary is that for thermofield double states, you can take the spectrum of the theory. For example, for many chaotic theories, you know the spectrum, or you know the statistics of the spectrum, at least. From that, you may compute the partition sum, and you have to analytically continue that. From that, you can compute this thing that I call the survival amplitude. From that, you can compute this Lanczos coefficient, Lanczos. It's a Hungarian name. Lanczos coefficients and the Krylov basis. And from that, you can compute the spread, quote unquote, complexity. There is precedent, by the way, for calling this complexity, because that's a notion, a related notion, has been discussed quite a bit in condensed matter physics lately, right? So that was actually the source of us thinking about this. So as I said, the value of trying to do a thing like this is in what it gives you as answers. So we can do applications of this to the SYK model and to various kinds of matrix models. And the reason to do that is we have a lot of evidence that these kinds of theories are related to two-dimensional gravity, that they have chaotic properties, and things of this nature. So we can examine in particular the chaotic SYK models that are dual to JT gravity, or are related anyway to JT gravity. And they have, as we know, similar kinds of spectral statistics to either the GUE or the GOE or whatever, one of these ensembles. And here's what you find. Suppose you go through this whole process and you work out the complexity as a function of time. You can see that universally, in all of the different systems we studied which are chaotic, there's an initial quadratic growth, which you can show analytically. Then there is a linear growth. The linear growth persists for time of order e to the entropy, right? And those people who've been following the various conjectures regarding black holes and everybody and things like that will recognize that that was what people wanted to see about the growth of something well past the thermalization timescale. Interestingly, this comes to a peak and then ramps down for a bit and then hits a plateau. The structure of this plateau, of how it meets the plateau, depends on whether, if you're doing matrix models, if you're in the GUE, the GOE, or the GSE ensemble. In one of these, there's a sharp transition. Another one, there's a smooth transition. Another one, there's a sort of oscillation of this kind. And those people who followed the discussions of things like the dip, ramp, and plateau in the, for the SYK model and in the statistics of the spectral form factor will also recognize some of those things happening and as being related to spectral rigidity in the, the structure of the correlations in the spectrum of the matrix model. So what are we seeing here?
This is true for any state that you choose to start from.
So that had to do with various questions that people asked. It's of course not true for an energy eigenstate. And this is strictly true, as shown, for the thermal field double state. So in the language of the duality with gravity, this is for a situation where you have the bulk black hole and stuff like that. But I would like to make an additional assertion that we will hopefully finish writing out soon. That is for almost any initial state, and I'm saying almost any, because the typical state in the Hilbert space involves some random coefficients distributed over your favorite basis. Pick any old coefficients you want, right? So long as most of the coefficients are not 0, right? It's going to be the case that after a short period of time, where this quadratic growth is not universal, you stick to the ramp and grow and come down in these theories. So this is universal in that sense of universality. So I think that's very cool. It's a fact that I didn't know about how wave functions spread in quantum mechanics. And I think it's true about chaotic systems. And you can also see, and we did some examples of integrable systems like particles moving on group manifolds and things like this, where you can calculate everything exactly. This does not happen in integrable systems. So I think this is an extremely simple set of statistics involving the spread of the wave function over a distinguished basis. The minimizing basis, in this sense, is a beautiful and very precise diagnostic of these different kinds of dynamics. That's it.
Thank you. Okay, we have time for a question or two.
So for systems that are not chaotic, which piece of these curves are not there?
So the ramp up, so it depends, because once they're not chaotic, they're not universal, right? There are many details. So the plateau won't happen quite like that. It can. You can have a plateau that depends upon if you're strongly interacting or not. The quadratic growth and linear growth, it sort of depends upon the details of dynamics. So depending upon, for example, if you look at a free theory, or if you look at, the particle in SL2R, the particle moving in SU2, things like this, you get, every piece of this can change. You certainly don't get the ramp up to exponential time and then a dip down to a plateau. So that none of that happens. I can't give you a precise answer because so far that we don't have a taxonomy. We did examples, and so basically, if you look, this was a paper with, I should have said, with Javier Magan, Pavel Kaputa, and a very fine student, Qingyue Wu. And if you look in our paper, we do many analytical examples that are integrable, and they all have different behaviors. So I don't have a taxonomy for you.
Right. Yeah, it was a great talk. If I compare your first two classes of complexity definitions, I mean, so there's the geodesic, Nielsen kind, and then there's this drill-off spread kind, and they seem, the first one seems quite a bit more complicated in my mind, and, for a variety of reasons. But it's the one that the computer scientists, I think, are much more interested in.
So let me tell you what relationship they may have. Can't swear to it, but they may have. So first of all, I would like to say the computer scientists haven't paid attention to this because they haven't known about this. But they should know about it, because it's giving similar information in terms of how the complexity grows in some sense. I think that's a statement to be proved, but this is so easy to calculate that they need to do this some of the time. So let me explain what happens with the other things. So what we want to do is you want to compute geodesics, right? So what you want to say is that the geodesic distance between the identity and e to the minus iht. So the way you compute geodesics on a group manifold is using something called the Euler-Arnold equation. And what you can do is you need a special metric. And the way you can write down a special metric on this, the complexity metric, you can say Gij is, let's say, the Cartan killing form plus Ci plus Cj over 2, where depending upon, if I is a complex or simple direction, you take Ci equals like e to the epsilon s for complex directions, and Cj is order 1, let's say, for simple directions. You set up a metric like that. So the problem is solving this. So it turns out that, this is actually a practical formalism. You can make progress, okay? So you can show that universally, if you measure this geodesic length as your form of complexity, there's an initial linear rise. So you can guarantee that there's a linear rise. Almost done, right? That's the statement 1. Statement 2 is, well, what truncates this rise? So there are 2 ways you could truncate this rise. If this is the group manifold, you could have this as a geodesic, and then you could come around the other side, and that may be shorter. There may be geodesic loops that you have to worry about. Geodesic loops are global properties of this manifold. This is a complicated fiber bundle. They're hard to solve for. But actually, there's another class of obstructions, which are what are called conjugate points. A conjugate point happens when there's another trajectory which sort of goes off like this, and that you can deform into this. That's a shorter trajectory. So there is a local equation for finding a conjugate point. The local equation for finding conjugate, it's like finding saddle points. So what you do is you perturb this a little bit. And if a first order perturbation of your geodesic solves the geodesic equation to first order, then you know that there's a nearby conjugate trajectory, conjugate point trajectory. You haven't found it, but you know it's there. So you can that's an equation that you can solve, and you can set up a criterion for it. And so in a paper with Onkar Parikar, Arjun Kar, and Kathy Lee, we do that, and we find that there's a detailed set of criteria for when and where these conjugate points happen, which are related to the spectral statistics of the theory. So and you can do that, and in particular, there's also a criterion that we call the eigenstate complexity hypothesis in honor of the eigenstate thermalization hypothesis. You remember which basically winds up saying the following thing. So it turns out that you can guarantee that the conjugate points will be pushed off to exponential time like this if no simple operation will move an energy eigenstate into another energy eigenstate. So in other words, if the overlap between the energy eigenstate m and the energy eigenstate n with an operator sandwiched, summed over all operators in the theory and normalized in some way, is less than some bound, you can guarantee that this linear growth will persist to exponential time. So this is a statement not about energy eigenvalues, but about in some sense, about the complexity of the eigenstates, how difficult it is to go from one to the other. So you can apply this again to the SYK models and things like this. And you can show that if you have integrable SYK models, you can guarantee that this growth truncates. It doesn't go up to exponential time because there's a geodesic that appears at polynomial time that truncates the growth. You can show that for free theories, we actually answered some question from computer science about whether you can do what are called Hamiltonian speedups. There's a question in quantum computation about whether you can get a shortcut to make things shorter. So you can answer that, and you can also show that for chaotic SYK, it persists forever. Kurt's signaling that I need to stop because Jomi needs to talk.
Okay, so we need to thank you.